Jai Hind everyone. Today I, Anshul Kumar Panchbhaiya, Assistant Professor Mechanical Engineering Department AKGEC, is going to discuss a topic named as column and strut. And this topic is very important for students studying strength of materials, especially in 5th semester. Previously, we have gone through the content that what is introduction of strut and column, that any vertical member subjected to compressive load and failing by lateral bending is known as column. Then column are of three types. The column is subjected to three types of equilibrium: stable, neutral and unstable. Stable means on removal of load the column is coming back to its original position. Unstable means on removal of load the column is not coming back to its original position. And neutral means that on removal of load the column is attaining some other position of equilibrium. This we have discussed. Then types of column is being classified on the basis of these three categories: short column, medium column and long column. And basically these three categories are being identified on the basis of a term named as slenderness ratio, ratio of equivalent length to the least radius of gyration is known as slenderness ratio. That is SE basically is termed as LE by K. Then we have seen the different end condition. A column subjected to, there are four possible conditions for a column. That one is both ends are hinged, one is one end fixed and other end free, the other is both ends are fixed, and the last one is one end fixed and other end is hinged. The long column theory is been given by, you can say, Euler's theory. Euler has given a theory of buckling, and these are the assumptions given by Euler. That first assumption is column should be initially straight, column cross section is uniform throughout, the line of action of compressive force coincide exactly with the axis of load, axis of the column, material is homogeneous and isotropic, and the column is basically the contraction in the column is due to compressive load is negligible. Means we are considering that the column is going to fail only due to buckling, not due to compression. Then this is the sign convention, that on if we are applying the load and the column is changing to this condition, then the moment will be taken as positive. If it is taking to this condition, the moment will be taken as negative. Means one is a convex shape and this is a concave shape. Concave is negative, convex is positive. Here I have told that this is negative. This is negative. Now this was the first case which we have discussed. What we have seen here, this is a column subjected to hinged load. Now from our slope deflection equation, we know that m is equal to EI d square y by dx square. This is our slope deflection equation. Now the column is subjected to hinged and hinged. Both points are hinged. A and O both are hinged. At a distance x, you have considered a section which is having a, you can say, a deflection of about y. This is a y deflection. Now if I consider this figure separately, which I have drawn here, so this is the shape I am getting. If I write the moment about this particular section, I will be writing EI d square y by dx square, but as per our sign convention, m should be negative, and we know moment is load into distance. So what is the load? Perpendicular distance, load is p, distance is y, the moment is p into y, and this will be taken with a negative sign. Negative sign indicates due to sign convention we are taking it as a negative. Now shifting the term to the right side, solving the differential equation which we have seen, and we have got the result. Finally we got the result, this pi square EI upon L square. This result we were getting, and this finally this result, in this result, what is P? P is nothing, it is a crippling load or the buckling load, and L is equivalent length and L is original length of the column. So this we have discussed previously. Now what is in second case? In second case, one end is fixed and other end is free. one end is fixed and other end is free. You can see in the figure, one end is fixed and other end is free. Same procedure we are going to repeat. What we are going to do? We are going to consider a section again, x, at a distance x. We are going to write the moment equation for this section. We are going to solve the differential equation, and then finally we are going to get the result. The only objective in discussing column is to achieve the value of crippling load. This is also known as PCR. This is the only objective. While you are solving any case, you need to find this value. Now what we are going to do, see the procedure is again the repeated procedure. I am going to write the slope deflection equation. If I see the slope deflection equation, I have written m is equal to ei d square y by dx square. If I am going to write the value of moment, what I can write? See, this is the distance a, this small distance is y, the remaining will be a minus y. If I write moment, it will be load into distance, it is p into a minus y. So I have written it p into a minus y. Why we have written it as a positive? Because it is having a convection. So it will be taken as a positive. So arranging these terms means pa into y can be written as pa minus py. This minus py taken to the left hand side will get plus py equal to pa. Dividing the entire equation by ei, you are going to get this term. If I replace this p by ei with a constant named as alpha square, so alpha square will be equal to p by ei. Now the solution of the differential equation will be this: y is equal to a sin alpha x plus b cos alpha x plus p upon ei a by alpha square. See, in the previous case we have done the same thing. What we have done? We have calculated the value of moment. We have replaced it with the help of ei d square y by dx square. Then what we have done? We have rearranged the equation, solved the differential equation and got the answer. This is the value of y. Now you can see here the constants are there, a and b. What we have to do? We have to calculate the value of these constants, and the one and only step is to get the value of this constant by using the boundary conditions. By using the boundary conditions. So what we are going to do? We are going to apply different boundary conditions. So what can be there? As you can see, if I apply boundary conditions for calculating the value of different value of, you can say different value of the constant, what I have done here. I can see at x equal to 0, if I am at this point, at x equal to 0, y is 0. Put that value. You replace x by 0, 0, 0, this is x, and y is 0 again. On solving this, you get the term, because we know cos 0 is 1, b plus a equal to 0, you will get b equal to minus a. Also, we know from our strength of material knowledge that at fixed point, if x is 0 and y is 0, also at the fixed point the x is 0 and slope is also 0. That means x at x equal to 0, dy by dx is 0. What you need to do? You need to differentiate this term, dy by dx. On differentiating it, I am getting the term dy by dx. Putting that value equal to 0 means on differentiating this term and putting that dy by dx equal to 0, what you are going to get? You are going to get a equal to 0. You are going to get a equal to 0. Now you have got the value of both constants, a and b. This is simple calculation, nothing more than that. You can see here, on putting the values, get the answers like this. These are the constant, nothing. What you have done? You have replaced dy by dx equal to 0. You know the value of b equal to minus a. On solving and rearranging, you get the value of capital A, and that you are getting at a 0. Now, what happened to our equation? Now, on putting the value of a equal to 0 and b equal to minus a in this equation, we are getting this. We are getting this, that is a into 1 minus cos alpha x. A into 1 minus cos alpha x. Now, if you see this figure, and if you observe this figure at x equal to L, if you are moving from this point to this point, you are traveling the distance L. This is x. At x equal to L, y is equal to a. Now, if you write x equal to L and y equal to a in this equation, what you have written? In place of y, you have written as a. In place of x, you have written as L. You will get this term. But you are getting cos alpha L equal to 0. Cos is 0 as 90, 3 pi by 2 and 5 pi by 2. Taking the least value, first value, you are getting alpha L equal to pi by 2. Alpha L, squaring both sides, alpha square is equal to pi square by 4. Replacing alpha square by p by ei, you are getting this term. Now, in previous case, you were getting pi square ei by L square. Now, you are getting here pi square ei by 2L square, and 2L is replaced by Le. Now, in this case, that means in this case, Le is equal to 2L, means equivalent length is equal to the twice of original length. In previous case, equivalent length was equal to the original length. So, this is the derivation you are getting. The similarity between both the derivation is what you are doing. You are just calculating the using the equation slope deflection, then calculating the value of moment by using the sign convention. After that, you are applying the boundary condition, and after applying boundary condition, you are getting the value of constants. On replacing those constants, you are getting the results. This is the procedure. In every derivation, if I take the different case, both ends are fixed. If both ends are fixed, what is happening? Same procedure, differential equation. See, this is the differential equation replaced by the moment value. The thing is here, in case of fixed case, there is a moment also. If you draw the FBD of a fixed support, you get a moment also. Now, you get the differential equation, applying the boundary conditions, solving it, means same procedure is going to repeat. This time you are going to get the result like this. This time you are going to get equivalent length half of original length. Equivalent length half of original length. See, first case you were getting first case L equal to L. That both ends were hinged. When both one end was fixed and one end was free, L equal to 2L you were getting. Now, when both ends are fixed, L equal to L by 2 you are getting. Now, if I move further, next case, if I say in case of both end fixed, one end fixed and one end hinged. So, this is now one end fixed, this is one end fixed and other hinged. In this case, same procedure you are going to repeat. You are going to calculate the value of moment, you are going to replace it using the boundary condition, same procedure, and again lastly you are going to get the value like this. Now, you are getting L equal to L by 2. So, in all cases you are getting the different values of equivalent length. In these four cases, one of the case oftenly used to come in end semester examination for solving or for derivation purpose, and it's very simple to do. If you know one case, you are easily in a position to do the rest of the case, because you are just, your value of moment is changing, thus just rest the step procedure is same, procedure is entirely same. All right. Now, if you see, there are certain limitations for a Euler's theory. Certain limitations for using the Euler's theory. The Euler's theory, the first limitation which is written is the Euler's formula is derived on the basis of assumption that the struts are initially straight and load is exactly axial. In practice situation, if you see what I have written in the first point, the Euler's formula is derived on the basis of assumption that the struts are initially straight and the load is exactly axial. Now, see, what is the question is here? Basically we are assuming we are assuming that our column is failing only due to buckling, but that is not the entire case. Sometimes the column may fail due to crushing also. But Euler says that if you are applying the Euler's theory, the material or the column will fail only due to buckling. So what parameter is going to decide that whether the column is going to fail due to buckling or whether the column is going to fail due to crushing? See, in the second property it is written, there is no strength property of the material of the state that exists in Euler formula. Only E is involved, which represent the stiffness characteristics of the material. Now, if we have to decide whether we are going to see that the column is going to fail by buckling or by crushing, only one parameter helps us in deciding that, and that parameter is known as slenderness ratio. This parameter also helps us in deciding that whether the column will fall in short category or whether the column will fall in long category, that whether the column is a long column or whether the column is a short column. Now, if you see this, what I have written, sigma C, we know stress is equal to load upon area, sigma crushing is equal to PE by A, pi square EI means P is equal to pi square EI upon L square, equivalent square, I is equal to AK square, and you are getting this term as what you are getting. In the bottom you are getting LE by K ka whole square, that LE by K is nothing, it is known as the slenderness ratio. This parameter is going to decide that whether the column is going to fail due to crushing or whether the column is going to fail due to buckling, or rather I would like to say whether the column will fall in a long category or whether the column will fall in a short category. So if you see this curve, what I have shown here, this is a curve, and basically this curve is drawn for steel. Now you are seeing this curve is like this, something like this, and in the y-axis you are having SYT yield strength and tension, and LE by K in the x-axis, that is your slenderness ratio. Now what this slenderness ratio says, if your value of LE by K is beyond this region, is falling in this region, then the column will fail due to crushing only. And if it is crossing this value, this point E, then the column will fail due to buckling only. So you have seen in the previous slide what I have written here. If I go previous, see what I have written here, the column categories, short, medium and long. So these categories has been decided on the basis of the slenderness ratio. So if I see the current diagram, I can say that for the long column the value should be in the region of, in this region. So what is for this region? If the value is falling in this region, then you can't say that the component will fail only due to buckling. It can fail also due to crushing. See what I have written, if OD represents the yield stress, OD, what is OD? This yield stress. Obviously the Euler formula cannot be applied if LE by K is less than OE. Means if LE by K is less than OE, means if you are in this region, then the column, in the column you can't apply Euler's theory. What theory then you can apply? The theory that you can apply is known as Rankine-Gordon theory. If you see where you are taking the failure due to crushing also. Previously you are assuming that the column will fail due to Euler's load only. But here the column can fail also due to crushing. So also due to crushing, if you take this load also into account, then this load will be represented by, this total load will be represented by crushing load plus Euler's load. Crushing load plus Euler's load. So the equation will become like this. Total load in the system was previously 1 by PE, but now 1 by P, because we know the column can fail also due to crushing, it will be like this. It will be like this, where P is nothing, it is Rankine crippling load, because this is Rankine formula. This is Rankine-Gordon formula. Basically this formula is given by Rankine. What is PC? It is the ultimate load, because the load which is making the load compression, which is producing compression in the system. PE is Euler's load, crippling load, where PE is pi square EI by L square. Now you read the statement. For a short column PE, the Euler's crippling load is very large. For short column crippling load is very large. Therefore 1 by PE is very small. It will be like this. If you see the statement, what is the statement has been written here? For short column PE, the Euler's crippling load is very large. Therefore, if PE 1 by PE is very large, if crippling load is very, what is crippling load? It is PC. PE is very large. Therefore, 1 by PE will be very small. It will be small. If this term becomes very large, this entire term will become very small. And then as compared to 1 by PC, then that time P will be equal to PC, means the load will be replaced by crushing load. And similarly for long column, PE is very small. If it is very small, then 1 by PE is very large. Then crippling load is equal to 1 by PE. The point is, if you are taking a short column, maximum case it has been observed, in case of short column the failure is due to crushing. So you take PC into account. But in case of long column, you take PE into account. And how PC, how PE, it has been decided by the slenderness ratio. So if I see the equation, what I have written here, 1 is equal to 1 by P is equal to 1 by PC plus 1 by PE. This load can be replaced by this term easily. If you divide the entire numerator and denominator by PE, you are getting this term. See, P will be deducted, this will be deducted, and this will be like this. Now in above equation, if I replace PE by this term, because we know the standard formula is this, and PC by this term, on replacing you are getting the value of this. Now what is A here? A here is known as the Rankine coefficient, whose value is equal to sigma C by pi square E. And in this concept, maximum time numerical used to come in end semester exam. Numerical used to come in end semester exam. What I have done here? I have done nothing. I have written the equation. I have taken, why I have taken the crushing load? Because the column may fail due to crushing now also. It is not failing only due to Euler's load. So P is equal to PC. Now on solving this equation, you are getting this term. Dividing the numerator and denominator by PE, you are getting this term. Now replacing the value of PE is equal to pi square EI upon LE square. PC is equal to sigma C into A. Putting the values, you are getting this value. Now the important thing is, you need to remember this coefficient. What is this coefficient? This is Rankine coefficient. So Rankine formula basically comes into account when there is a short column or failing due to crushing. Long column fails due to buckling and short column fails due to crushing. Now this is again another straight line formula. This is known as straight line formula for calculating the load if the crushing is there, and Johnson's parabolic formula for solving the numerical, for calculating the load. Maximum time the numerical used to come from this formula, which I have circled here. Rarely these two topics has been asked, but still we need to know that there are some formula like straight line and Johnson parabolic which helps us to finding the load also. Now till now what we have done, we have only considered the load passing through this axis. What happened if the load is not passing through this axis, if it is at a certain distance E? See what I have written here, an eccentric load. That loading condition is known as eccentric loading condition. the load is not passing through the axis of the column. It is at a certain distance from the axis, and that axis is known as, that loading is known as eccentric loading. Now you have seen an eccentric load is that which does not pass through the centroidal axis of the cross section of a column or a machine member. Such load always produces two effects, primary and secondary. What it is talking about? See, I would like to explain this concept with the help of this figure. See, suppose there is a load P and this is a point O. If you transfer this load to this point, this can be done by using two steps. At this point O, apply same amount of load in upward direction, same amount of load in downward direction, upward direction. These two will going to produce a couple of amount. Suppose the distance is L, P into L. So final diagram will be like this: downward load P and this moment of P into L. So what I have written here, such a loading always produces two effects, primary and secondary. So this P is primary effect and P into L is the secondary effect. What you have done? You have transferred this load to this point. So if there is an eccentric loading, there will be primary and secondary effect. So short column, if you are talking about short column, if you are talking about short column, you can see here a column of a rectangular cross section. Now, a rectangular cross section of width B and depth D. So the resultant stress will be the addition and subtraction of the direct stress plus direct stress and buckling stress, sigma B and sigma D. This will be the resultant stress. See, in case of its short column, if no buckling has taken place, then the resultant stress will be like this. Now, what I have told you, this is the diagram which I was telling you, that this is a load. If you are transferring this load, this load will be composed of two things. One, the load transferred to the centroidal axis, and the other, the moment which will be produced by this load, because finally you need to transfer the load to the center. See, this diagram is indicating this. Now these two will produce a couple of P into E, and this is the P. So this is the primary effect and this is the secondary effect, which we have seen in the previous slide. The effect simultaneously, that is the primary and secondary. See the line. Effect is primary and secondary. So now this diagram is showing the variation of stress. Now this moment is replaced by P into E. See, in previous slide I was writing this P into E. Now in the next slide I have got this P into E. This moment is P into E. This is a linear variation. Now if you see the variation is linear, then what you need to remember? You need to remember that whether the loading is eccentric, then there will be two forces working. One is primary force and the other is secondary force. One is primary and secondary. So if anyone is having little bit confusion, let me explain this thing. If there is any load, like this P, and you need to shift this load from this point to this point, you need to shift load from this point to this point. What do you need to do? If you are, suppose this is load working at point B and you need to shift the load at point A, you apply same amount of load in upward and direction and downward direction in point A. Now observe which of among these three forces are working equal and opposite and parallel to each other. So this and this will be working equal and opposite and parallel to each other. So these forces are going to generate a couple. These forces are going to generate a couple. So this couple have a magnitude like this, P into E. So final diagram will be like P is equal to P into E. So this P will be primary force and this will be secondary force. I hope you all have got the concept. So this was the concept I was trying to explain. In the next lecture, we will go little bit further on this topic. Thank you. Jai Hind.